It is a privilege and honor to introduce Professor Kaie Kubjas. Uh, Professor Kaie Kubjas did her PhD in the year 2013 from the Free University of Berlin under the supervision of two real giants of the area of algebraic geometry. One is Christian Hasse and the other one is Klaus Altmann. And these person does not require any introduction when we talk about the area of algebraic geometry and commutative algebra, and particularly in algebraic geometry. And moreover, after the completion of her PhD, she got affiliated with Aalto University. Before that, she was in Sorbonne University in France too for some time. Let me just tell you, Sorbonne University is a very special university in terms of mathematics. Her research interest is quite diverse. She worked in algebraic geometry, algebraic statistics. Particularly, she dealt with the application of algebraic geometry in biology, and particularly something regarding to the reconstruction of 3D genome by using algebraic geometry. Her affiliations with CIMPS and other administrative things. She is the deputy convener of the European Women in Mathematics. So this is a very, very special day. I hope every one of you are already familiar with. Today is the International Day of International Women Day, and we have Dr. Kubjas with us, and we are opening our day with Kaie, and who is the deputy convener of European Women in Mathematics, and she is the secretary of the CIAM. CIAM is a very, very big firm which promote scientific sciences and industrial and applied mathematics, and it has particular divisions, and she is the secretary of the division of promoting activities related to algebraic geometry. So she's the convener of, she's the secretary of CIAM activity group. Today, okay, regarding to her lectures in this CIMPA school. So she already wrote something on the board. Let me just go. So she's going to tell us something about geometry of non-negative matrix rank. So her lecture, definitely this is a topic that not everyone is familiar with, including myself. So let's listen and let's learn this topic directly from Kaie Kubjas. Kaie Kubjas, thank you very much for accepting our invitation and coming all the way to Pakistan for this CIMPA school. Welcome to Pakistan and welcome to this CIMPA school.
Thank you very much for the kind introduction. I would also like to thank the organizing committee and the scientific committee for really excellent work that they have done organizing this conference. And I'm very grateful for the opportunity to be here and spend this week with you. So I will have 4 lectures. I just wanted to check, is the microphone working? Can you hear me? Good. So as Professor Anwar said, you might not be familiar with the topic, so I really will try to start from the beginning. And actually, I will start with something that you will probably know. So I am sorry if I'm going to bore you for the first 5 minutes, but I want to make sure that everyone's can follow from the beginning on. So I will actually start with linear algebra. So let's get started. So the topic of today's lecture is non-negative matrix factorizations and non-negative rank. So today we will start with the basic definitions. Then we will see some basic properties. And today is like, we will talk about applications. So today is the least algebraic and geometric lecture. And then in the next 3 lectures, we go more into the topics of algebra and geometry. Okay, so but let's start. I said the first 5 minutes might be boring for you because I want to recall a characterization of rank from linear algebra, because I'm going to recall a version that might not be the most commonly used version of rank. And it will be an exercise for you to prove that this is equivalent to the definition that you're familiar to. So the rank of a matrix M, and in this lecture we'll talk only about real matrices with real entries. So M times N matrix is the smallest integer k such that M can be factored as M times M equals A times B, where A is a M times K matrix, and B is a K times N matrix. So M was M times N matrix, and we factor it as M times K matrix times K times N matrix, and A and B are with real entries. And this definition or characterization would work also over other fields, but non-negative rank, when we talk about non-negative rank, we talk over reals, so I restrict to reals. And as I said, exercise is prove that it is equivalent to a characterization that you're familiar with. For example, that the rank is the number of linearly independent, the maximum number of linearly independent rows of the matrix, for example. Okay, so, and the reason why I'm writing it here is because when I'm going to define non-negative matrix factorizations and non-negative rank, then it's closely related to the characterization that I wrote here. The only difference is that now we will require that these factors A and B will have non-negative entries. So, and I actually want to start not immediately with non-negative rank, but I will start with non-negative factorizations. So given a matrix M, and now require that the entries of M are non-negative, and it's an M times N matrix, a factorization so M equals A times B is called by size R non-negative factorization of M if A is an M times R matrix with non-negative entries, and B is an R times N matrix with non-negative entries. So we have factorizations similarly as in the characterization of rank, with the difference that the matrices that we consider have non-negative entries, and the matrices in the factorization have non-negative entries as well. And let's do an example. And please stop me anytime if you have any questions. And this is in some sense very simple example. Let's consider this 0, 1 matrix. Can you see here, or should I write? Okay, then and we can write it. Times the identity matrix. And a very simple question to the audience: what's the size of this non-negative factorization? I heard 4 somewhere, so it's correct. And the reason why it's 4 is because this matrix has 4 columns, or equivalently, this matrix has 4 rows. And it's a non-negative factorization because all the entries of this matrix are non-negative. But of course, this was not very interesting factorization because I just took the matrix itself and multiplied with the identity matrix. Okay, but for an example, it's fine. Okay. So this is first very important definition. And then second, so let's say these are the 2 most important definitions. The second one is not of non-negative rank. So maybe you already can guess what's coming here. So the non-negative rank of matrix M and with non-negative entries and size M times N is the smallest natural number R such that M has a size R non-negative factorization. And notice that, so maybe I'll give you 30 seconds to finish writing it. So this definition is very analogous what we saw here, only I've written it in 2 steps consisting of 2 definitions. But if I wouldn't write it in 2 steps, then another way to write rank is exactly like here, only we add everywhere that all the matrices have to be non-negative. So it's really very analogous to a characterization of rank in linear algebra, but now we have this non-negative rank. And although I'm not going to talk about in this lecture, there are other ranks. So one considers also a positive semi-definite rank, and there are conic ranks. So this is not, let's say, only analog to the rank from linear algebra. Okay, and then example. So many of these things that I don't prove right now, we can discuss those either in discussion sessions or in the tutorial. So now I'm going to make some statements that I'm not going to prove right now. So yes. Oh, sorry. Let me write this example 1 so that I can refer to it. The matrix in example 1 has non-negative rank 4. So I'm claiming all that I wrote here, this boring factorization, where I took the matrix times the identity matrix, I'm actually claiming you can't find a factorization where it would take only 3 columns here and 3 rows here. And right now, I would say it's also quite difficult to prove it. So we will learn a geometric characterization of non-negative rank that makes proving this much easier. So this is one statement, and this is something that you should be able to show, is that this matrix has rank 3. So it has rank 3. And so let me write down a size 3 factorization. And if you look carefully, what I've done here, I've taken the first 3 columns of this matrix. And this matrix just tells how to write all the columns in terms of this matrix. And as you can see, so in this case, the non-negative rank is greater than the rank of this matrix. So this is one property that always holds. So next I'm going to list some simple properties of non-negative rank. And I think I forgot to, so let me write down somewhere that how we denote. So non-negative rank of M is denoted rank plus M. Okay. So some properties. And if you're wondering why I'm talking about all of this, so then just wait 5 more minutes. Then I'm going to give the plan for the all 4 lectures. So then it also becomes clear, maybe more clear why this notion is interesting. So and the n times n matrix with non-negative entries. So first, we always have that the non-negative rank of n is greater or equal to the rank of n. And this follows actually directly from this characterization of rank and the definition, but we can discuss it, the details during the tutorials. Then second property is that the non-negative rank is always lesser or equal than the minimum of m and n. And I think this is quite simple to show, but I think this is a very nice exercise to prove it. And then third property is that if rank of m is 0, 1, or 2, then non-negative rank equals to the rank. And the cases 0 and 1 will be exercises again. The case 2 is trickier. So 0 and 1, all of you, I believe, can do it. And I think for the 2 case, we will first need to learn some of the geometric tools before. And once you know the geometric tools, then the proof becomes very easy. But I think without these tools, at least for me, it's not so easy to prove. Okay, so this will be exercise. Prove these properties. So, and as I promised, next I will tell you about the main codes for the lecture series. There is a question.
There is some confusion. You have written this matrix into A into B, where B has a negative entry.
No, on the right side. On the right side. Sorry, this is very good question. So here I talk about rank, and for rank we don't have the requirement that the entries need to be non-negative. So here I just wanted to make the contrast that its non-negative rank is 4, although I haven't proven it. I've just given a size 4 factorization, but I haven't proven that it doesn't have a smaller factorization. And here it's just I'm giving a size 3 factorization, and it's very interesting because it has 1 negative entry, and it's only 1, but one can't get rid of this 1 negative entry. So did I answer your question, or okay? Then the plan for the lectures, plan for this week. Or let's say this is the original plan, maybe we have to adjust. So the plan for the second lecture is geometric description of non-negative matrix factorizations. It turns out that I gave you right now an algebraic description. It turns out that non-negative factorizations and rank can be described using polytopes. And I'm very thankful that Dean Lei gave such an excellent introduction to polytopes yesterday. So make sure that you understand yesterday's lecture of Dean Lei very well. So this will be helpful tomorrow. So geometric description of, and when I write N and F, this is non-negative matrix factorizations. I will use this abbreviation a lot. Using polytopes. Actually, it's using polytopes and cones. And then the third and fourth lecture, they will be related to real algebraic geometry. So second lecture is with polyhedral geometry. Third and fourth lecture are real algebraic geometry. Of matrices of non-negative rank at most R. And I think most of you here are familiar with algebraic geometry. So in real algebraic geometry, we consider subsets of R that are defined using polynomial equations and inequalities, and then some combinations of this. These sets are allowed. So this is lectures 3 and 4. And in the rest of the lecture today, I will talk about applications. And I hope that by the end of the 4th lecture, you will see, and what really fascinates me about this topic, we really need tools from algebraic geometry to prove results that are useful in applications. And like for this, you need algebraic geometry, you need polyhedral geometry, and I think this is like really nice how pure and applied mathematics combine. But that's why I want to tell you also about applications, so you can see, you know, motivation for some of these things that we are doing. Okay, so
just a few comments on the non-negative rank function, because you are interested in non-negative entries because they have the combinatorial instruction.
So there are different reasons. Some of the reasons will become clear when I talk about applications. Often the non-negative entries have some interpretation. For example, when we talk about images, it could be that we want pixels to be non-negative entries, for example, and if we would allow negative entries, then this wouldn't have nice interpretations. So this is one thing. So this data analysis is one motivation, but actually before non-negative factorizations became popular in data analysis, it comes from complexity theory. So so it's related to like complexity theory of linear programs, and there it also turns out that this non-negative entries somehow come up in the slack matrices of polytopes. So these are the two reasons, but usually it's the interpretation. Okay. And this is what I was just going to write. So I warned you that next half an hour will be the least algebraic part of this lecture. So what I just said, the main reason why people are really interested about non-negative matrix factorizations is that it is an easily interpretable. Linear dimensionality reduction technique. And I will tell you what these things mean. And now I will talk for some time about linear dimensionality reduction techniques, or like what does it mean? So one of the main questions in data analysis is extracting the structure of the data. And so linear dimensionality reduction techniques, which actually mean low rank matrix factorizations, is one approach to do it. So Let me already write here that I will abbreviate this linear dimensionality reduction as LDR, so that I don't have to write it out again. And one approach to extracting the structure of data is exactly linear dimensionality reduction. And what a linear dimensionality reduction does, it expresses the data as a linear combination of basis vectors. And we will see this is exactly low rank matrix factorizations. So so what does it mean? So this was now, like, let's say, a general story, but let's put it more mathematically. So given a data set of n points, and we denote these points by xj, and there are points in Rm. And these points will correspond to the columns of the matrix that we are interested in. And our aim is to find a small number of basis vectors wk, but also our vectors in Rm, and now k ranges between 1 and R. And in the notation that we used before, so this wk, they correspond to the columns of A, such that each data point is well approximated, and I'm going to be a bit vague here what this well approximated means. So it can mean several things. by a linear combination of basis vectors.
Excuse me,
Yes.
what are eta and n in the last one?
Given a data set of n points xj, so n
The range j varies.
j is between 1 and n.
1 n?
N.
N.
Yes.
They will define Rm. What is n?
So we have, so you can think of, let's do an example to clarify this. So for example, we could have 3 data points. So in this case, n is 3 because we have our data set consists of 3 elements, and m is 2 because these are vectors of length 2. And these 3 data points, they correspond to this matrix. So we think of it as this matrix where the columns are these elements in the data set. Okay. Yes. And more mathematically, so that we can write each data point as a linear combination of the basis vectors. So these are some scalars in R, and these are again vectors in Rm. So for all j, so and okay, this is maybe not so interesting example, but in this example we could, and I hope I'm doing it correct because so that was x1, that was x2, that was x3. And in this case, we could take our basis vectors to be 1, 1 and 2, 0. Then to write x1 as the combination of the basis vectors, we would take scalar 1 here and 0 here. For 2, 0, it's 0 and 1 here. And then, for 3, 4, I guess we need to take 4 here. And maybe minus 1/2 here. But this, we are not talking about non-negative factorizations yet, but let me maybe write down the coefficients for h. So h, 1, 3, I believe should be 4, and 2, 3 should be minus 1/2. Can anyone verify who is not on the blackboard if these are the correct coefficients? Okay. Sorry?
Independent, but
So, and in this case, it's exact. But here I wrote this well approximated. So in the applications, usually it's not exact, but one specifies some norm and then tries to, find something that almost gives xj. And as I already said, linear dimensionality reduction is equivalent to low rank matrix approximation. So what I wrote there in the matrix format, it can be written as, so we construct a matrix X. We don't construct, but our data set gives a matrix X, so whose columns are x1, x2, up to xn. And we want to write it as the product of two matrices. So the first one is a matrix whose columns are the vectors W. So, and this is now n times R matrix because we have R basis vectors in R to the n. And then this scalars HKJ, we can also write them in a matrix. And this matrix is R times n matrix. And just to be sure that we're all on the same page, let me write down once more. So each column of X corresponds to a data point. Each column of W is a basis element. And each column of H gives the coordinates of xj in the basis given by W. And maybe one more thing that follows from here is that we can write, if you take any column of the matrix X, then, and assuming we have equality here, but let me write maybe the approximation. This is W times Hj, where we take the j column here. So this follows directly from this matrix product, but sometimes we will use this. So this means that each data point can be written in terms of the basis W using the corresponding column of H. Okay. So far what I talked about had nothing to do with non-negative matrix factorization. So this is a general story. And if you're familiar with singular value decompositions or principal component analysis, this is all related to what I wrote here. It's a linear dimensionality reduction method, but there we don't require the entries of the matrices to be non-negative. And for PCA, I'm not going to talk about it, but I said actually you have to somewhere specify a norm. So in this case, it would be Frobenius norm that one specifies. So non-negative matrix factorizations are part of the same story.
So most of the time, this n is greater than n, right?
Most of the time, n, the number of data points is greater than, not necessarily. So I worked recently with a neuroscience dataset, and there we had 2,000 measurements in 10,000 dimensional space. So, and the 10,000 corresponded to the number of neurons where the spikes were measured. So I think not necessarily, but it could be. So an example that I'm going to do, like more specific example there, it's exactly, so I think it depends on the applications. Ideally, yes, and like n is much larger than m, but I think nowadays, let's say in neuroscience or biology, there might be very high dimensional spaces and maybe not so many observations. But I think classically it's like, let's say, before the times of big data, it was the case. Okay. But what will be true, and I'm going to make a remark, m and n are much larger than r for this to be interesting. Yes.
For instance, you're working with image data sets, so kind of image will be converted first to Apollo matrix for the image.
I will do the example, let's say in 5 minutes, in 3 minutes. But exactly, the images will be vectorized to columns of the matrix X here. Mark. Actually, R is much smaller. And M and N, which allows to compress data. What this means that this matrices W and H have less elements in total than the matrix X. And an easy exercise for you, enough to have R strictly less than m times n divided by m plus n. And you can have this bound by comparing the number of elements in this matrix and the number of elements in these two matrices.
Can R be greater than what? I mean,
Then there is one.
If R can be greater than
any of them.
well, then it's not so interesting anymore, because usually, like if R is great, so it wouldn't work for compressing data because you get more entries here, but also like this finding the structure in data, it also is not helpful anymore because we have some data set and we would like to find some like basis images or the structure of the data. And if R is greater than M or N, then we are finding something larger. So we are not extracting the structure of the data anymore. So in like anything that one does, R is less than minimum of M and N. Okay, so, and what I already mentioned, so far it was a general story, but different constraints can be imposed on W and H. Depending on the application. And we consider the setting when W and H are all entries are non-negative. And in the last 5 minutes of this lecture, I think I don't have time for 2 examples, but I want to do one specific example. And there's a question.
Actually, information from n number of points or data points, and we have now very less number. R is very less than n. Then what is the order of errors in this approximation? And how well is approximation?
Well, it depends on the data set. So I can't comment very much on this. It's very specific to data set, but then in many applications, often it turns out that the data for some reason is almost low rank, or like, you can really reduce the number of points. And there is even this one paper by, I think, Rachel Ward. This is about why often the data is low rank. So I can look up the citation for this paper. But yeah, so people have studied, why actually the data is often low rank, why this assumption makes sense. But I can't give you anything about specific error bounds, because it also depends very much on particular matrices. Okay, so let's do the image processing example. And this example comes from this very famous paper by Lee and Soin. In 1999, that was published in Nature. So that was, let's say, the starting point of using non-negative matrix factorizations in data analysis. So the history of non-negative matrix factorizations goes back to the 60s. I mean, without it being called non-negative matrix factorization, it was used in chemistry, and then in 90s it started being used in this complexity theory. But it was really the 1999, like since when it has been very popular technique in data analysis. So we already, this was mentioned. So now our matrix X. So we can think that the rows correspond to pixels. So we have n pixels, and the columns correspond to facial images. So different pictures of faces. Okay. And then in this case, what a non-negative matrix factorization does. So, and that was also a question already. So actually, we can think in this particular data set that Lee and Soin studied, they considered so quite simple images with 19 times 19 pixels. But then, so each column corresponds to a face. Right? But you ask, okay, here it's 19 times 19, here it's a column vector. So this image is factorized. So you have matrix, but then let's say you stack all the columns of this matrix on top of each other. And then you do this factorization where the columns correspond to are basis images. So it could be, for example, that one column corresponds to mouth, smiling mouth. So it's like somehow basic structures of faces, so that you can write your face images as a combination of these basic images. And then this last matrix, it gives the encoding, meaning it gives the coefficients how to write the faces as a linear combination of these basis images. But moreover, because all the entries are non-negative, this means no cancellation happens. So, and in this particular example of Leanne Seong, it was 19 times 19 pixels. N was 2,429 facial images. So exactly the setting that Professor Anwar was saying, that N is greater than M, and like traditionally this is the case. And the R, so the number of basis images they used was 49. So this is one example from their paper, and they have, let's say, two very important examples. The other one is about topic modeling. So I want to leave a couple of minutes so we have 4 minutes left, so I think I want to stop here. We can talk about the second example if anyone is interested during the discussion session. So the idea is very similar, but now instead of facial images and pixels, one has words and documents. And so it's a topic modeling example. And there are many other examples where non-negative matrix factorizations are used. And the main reason, what I already wrote before, why one would use this instead of ECA or SVD is because it's often interpretable if our data is naturally non-negative. And the disadvantage is that this is much more difficult to compute than SVD. And then to the end of this lecture, so I would like to show you this book. Last year, in the CIMPA data science book series, there was book Non-Negative Matrix Factorizations by Nicholas Gillis. And so everything that almost everything that I'm talking here, actually not the third and fourth lecture, there are more algebraic. So you can find in this book, and I really find it very interesting that it has many more examples. It has blind source separation, some other examples. So it's really an excellent book if you want to take a look. Yes, there is a question.
Can you write the name of the author?
Yes. So I'll write it here. So the title is Non-Negative Matrix Factorization. And the author is Nicholas Gillis. So he's actually a numerical analyst himself from background. And the book is from last year, so it's really very up to date, and it was very needed because the last book was like 10 years old, and let's say many of the results in this field are actually from the last 10 years. So this previous book is missing, let's say, many of the newer results. So I really recommend this book if anyone is interested. And what I find really nice, although he's a numerical analyst, he has tried to include some of the algebraic results, and so he really tried to include everything that's known in the book. Are there any? So I will stop here for today. Are there any? I think we have 2 more minutes for the questions. Yes.
Can you use this idea in the book? Can we use can we use this idea in cryptography somehow?
I have not heard of applications in cryptography, but I have to say I'm not at all an expert in cryptography, so it doesn't mean that there isn't, but I'm not aware, and I think this book also doesn't have applications in cryptography. I'm not completely sure, but I am not aware, but it might be, you know, something that's undiscovered. Yes?
How can we see if there exists a non-negative factorization of a matrix other than identity matrix?
This is the question we are going to address in the next 3 days. Well, let's say there are algorithms, there is different sides. We are going to take the algebraic approach, and this is exactly the motivating question, let's say, for many of the things that we are going to do. And then there is like computer scientists, they have like, you know, studied the complexity and they have like algorithms. So first like from theoretical algorithms, but then also numerical algorithms. And let's say if you want to do it in practice, there is code accompanying this book. You can see the link later on, like that has a, you know, there are some numerical methods if you want to actually compute non-negative matrix factorizations. But they are of course not exact. So this will be like approximate methods. Yes?
Is it easy for you to say why non-negative decomposition of components are important in this particular application?
In this application, so actually in this application it was black-white images. So the pixels are some certain values. I don't remember if in this case it's between 0 and 1 or like, so let's say 0 corresponds to white and black corresponds to 1. So this is the reason. And then this topic modeling, the example where it's words and documents, it's counts. So counts are again like how many times a word appears in a particular document.
Any other question by the audience? Maybe in IBA Karachi, would you like to ask any question? Is something there in the chat box, Noman? Okay, no negative. Okay, he already replied. Oh, okay. May you please comment about this bound of R, how it was discovered a little bit more?
So it's this one here.
Yeah.
Okay, so this comes. So this matrix has m times n entries.
Yeah.
So m times n entries. So this matrix has m times r entries, and this matrix has r times n matrix entries. And for data compression, we want that the number of entries here is smaller than the number of entries here for the data compression to happen. So, and this is equivalent now, m times n is greater than r times n plus n. And from this one gets that r is less than m times n divided by m plus n.
Thank you very much. Thank you. Okay, is there any other question? Okay, this is proven to be a very practical lecture series because okay, there are already people who have the interest in data analysis, and it will be very interesting to attend the upcoming lecture people will be waiting for. Once again, thanks the speaker for a wonderful lecture. Now it's time for tea.